Hi, my name is Janet Mitchell, and this is my presentation on the compactness of sets. First, I'd like to begin with the definition. Compactness is a property that a set can have that combines the properties of being closed and bounded. So, to be a closed set means that all of the set's limit points are contained within that set. We can see in our first few examples here on the table. The brackets indicate that the boundary values are included in the set. That's what we mean by closed versus open. A closed interval includes its boundary points, while an open interval does not. A bounded set can fit inside some finite interval, so there's a limit to how far the set extends. For sets that extend infinitely far, those are unbounded because they have no finite edge. So how can a set be closed yet unbounded? The key idea is that being closed is determined by limit points, not about going towards infinity. A set is closed if it contains all of its limit points. So even though a set may be unbounded, it can still be closed as long as none of its limit points are missing. So knowing all of that, the Heine-Borel theorem allows us to determine whether a set is compact by checking if the set is closed and bounded. So now the big question, why do we care? Like I said, compactness is a property. One way to think about it is that compact sets behave nicely, which allows us to prove a lot of important theorems. One example is the extreme value theorem. This graph shows a continuous function defined on a compact set, so that goes from -1 to 2. Because the set is closed and bounded, the function is guaranteed to have both a maximum and minimum value. If this set were not closed, a max or min could be missing. If the set were not bounded, the function could continue increasing or decreasing without ever reaching an extreme value. So this is one reason that the Heine-Borel theorem is useful. By checking whether a set is closed and bounded, we can quickly and easily determine whether it's compact. Moving into higher dimensions, I want to talk about the formal definition and what open covers are. An open cover of a set K is a collection of open sets whose union contains K. So what's a cover? A cover is a collection of sets that contain the entire set of K. I like to think of these sets as stickers. You can cover K with so many stickers, and it could be infinitely many. But within all of those stickers, which could be an infinite number, is a finite set, a finite subcover that covers all of X. Looking at our example, you can see all the sets E1 through E5 that cover K. And this set could be an infinite number of sets, but there is a finite set of those stickers that cover K. And in this example, we can cover K with just E1 and E3. This smaller collection is our finite subcover. Most importantly, every point of K must lie inside at least one open set in the cover. So that just means the set K must be completely covered with those stickers. Then there's a finite set of stickers that completely cover K. This leads to the formal definition of compactness. The Heine-Borel theorem then tells us that in higher dimensions, this is equivalent to the set being closed and bounded. This theorem is so powerful because if and only if is a very strong statement to make. It tells us that compactness and being closed and bounded are completely equivalent in higher dimensions. This theorem is useful because we can skip checking every possible sticker to make sure K is covered. Instead, we only need to check that K is closed, meaning it has all of its limit points, and is bounded, meaning it doesn't extend out infinitely. Rather than analyzing every possible collection of stickers that could cover K, the Heine-Borel theorem checks the set for closure and boundedness. If you'd like to check out a cooler video, I have one linked here in my PowerPoint. Another thing I want to talk about is connectedness, and it's not the same thing as continuity. Continuity is a property of a function, while connectedness is a property of a set. A connected set is one that consists of one single piece. In the first example, the intervals are not touching and are not a single piece, but the set is still compact because it is closed and bounded. In example 2 shows us the convergent sequence as a collection of points. This collection of points is infinite, but bounded because it converges to 0. The point 1 is included in the sequence, but 0 is not. And since 0 is the limit point of the sequence, the set is not closed when any limit points are missing. So when we add 0 to the set, it becomes closed because it now contains the limit point. Now that the set is closed and bounded, it is compact. Here are some practice problems to consider. Sets L, M, and N are defined here. For each set, determine if it's bounded and if it's closed. By applying the Heine-Borel theorem, the set must satisfy both properties to be considered compact. Thank you for watching my video and have a great day.